Hello. I am going to present my talk that was entitled Empowerment and Predictive Information, the Duality between Potentiality and Actuality and its consequences for the relation to an agent and its environment. But the title is a little bit too long, and so I decided to make it shorter. Coulda, woulda, shoulda. In other words, we can ask the question what an agent could do, what it would do in a certain state, and what it should be choosing to do. Of course, in the case that there are preferred actions to select from. So let me just summarize the scenario. This talk is a little bit of a perspective talk, but I want to create the setting in which we are operating. So if we look at a world, and let's for now just look at a physical world without an agent. And in that case, you can write the world as a, say, Bayesian network, it's basically a Markov chain in this case even, which is basically unstructured. So you have world states and they transit from earlier times to later times in this sequence. Now let's add an open loop agent. An open loop agent is one of the agents that, for example, Hugo Techet and Lloyd are looking, Seth Lloyd are looking at in their work from 2000 and 2004. And essentially, when you have an open loop agent, means this is an agent that chooses actions that influence the world, but there is no sensory input. So the agent does not use the previous world state to decide what they do. They have a stochastic policy that does the same thing in every step. So these arrows are all interlinked. And this is basically what makes an agent. And you can actually choose policies that modify the world dynamics in a tangible way as to achieve particular tasks, even without sensoric abilities. And when we talk about tasks, mostly what you can actually do, you can quantify to some extent what you can do with this type of scenario, is things like modifying the entropy of the world and changing that entropy, even with an open loop agent. That can be possible. Doesn't have to be possible, but it can be possible. We can improve on that in a measurable way that we know, in fact, how much Seth Lloyd and Hugo Techet have quantified that by taking in account what we can observe about the world. So this information that we can take from the world into the agent can change how much we can control the world. In fact, we can increase the amount of control. And this is, in this case, you are in principle allowed to access everything in the world. In reality, it will be only part of it that you will select, but in principle, you could select any information from the world. It gets more lifelike when you now start introducing a sensor. The sensor is no longer universal. You have no full access to the state of the world, but this is what real agents have to contend with. They have a limited sensor that hopefully captures the right features of the world, but it may not. So we have here a reactive agent that takes the world input, processes the sensory input, transfers it in a suitable way to the actuators, and influences the world again, and so on, and so on. And finally, we can extend that by an agent that's no longer reactive, but actually has a memory. So the sensor is processed, the sensor state is processed through the memory and affects the action, and it affects the next memory state. So there's a history to how the world looks like for this agent. So this agent can remember what happened before. Now, when you look at this, this is the most general single agent Bayesian network that you can imagine, with arbitrarily complex worlds, W, and arbitrarily complex memories, M. So they can be as complicated as you want. And you should notice that there is not only in principle a symmetry in time. I mean, of course, the time symmetry is broken because the world has a direction, the time has a direction. This is the reason for that is subtle, and in principle, but for us, the time direction, let's assume, is given simply by the direction of entropy increase. But the other symmetry, which is not as obvious on the first side is the symmetry along this axis, the sensory actuator um, membrane axis. And the reason for that is quite interesting. We don't have the time to discuss that in detail. However, it should be noticed that essentially there's full symmetry between the memory state and the world state in terms of structural symmetry. Of course, the memory state is much more condensed than the world state, which is much more basically physical objects, and there's much less compression in general than when you look at the memory. But structurally, they are essentially equivalent. And this duality is something that is interesting to explore. And I will very briefly touch on that later. So if you look at such an agent, a universal agent that has to solve some tasks, say reach a certain reward or cumulative reward in the environment, and you can ask, okay, how much information, when I talk information, I mean Shannon information, does the agent actually require to achieve that particular reward? So we're collecting rewards here, as you see the R's, and this reward, to achieve a certain level, you need information from the environment. And this is the amount of information we get. It basically, we change a policy that decides what information from the sensor, how we're processing it, and turn it into an action that will achieve that desired value. Now, this is the so-called relevant information. You ask how much of information is relevant to achieve my task, my utility at the desired level. And that can be at first, for example, considered just without considering memory at all, the memory transfer at all. So essentially, it's purely reactive, essentially. And this is basically how much information do you pull from the environment. So you can ask, how much information do I need to suck to pull from the environment to achieve that particular goal? This is what people use as relevant information. Now, you can now ask a dual question. Relevant information has a pretty obvious interpretation. It's basically asking, okay, how much information do I need to solve this task? It's very natural to ask this question. It's a natural question by now. It has been asked for now roughly 15 years in that form, and 15, 20 years, and essentially we can essentially many processes are basically costed in terms of this type of information. But you can ask a dual question. The dual question is the push information. It's basically the other side of the coin. It is, if I were to push information through the world, through the actions, to the sensor in the next state, how much could I do? What could I achieve at most? Now, notice relevant information is something you want to minimize. You want to minimize information, you need to achieve a certain value. Because if you increase it, it's expensive. You want the organism, the agent, to process as little information as possible. With a push information, it's the opposite question. How much information can I maximally push through the environment? Now, one would ask, why does this question actually make sense? The environment is not the receiver that cares about anything. Gibson observed that the environment is not a sentient being that cares about decoding the information you send it. Now, if you look at this, of course, the environment is not the ultimate target of this information. The ultimate target is actually the sensor of yourself, of your own agent at a later time step. Secondly, this information that you send to the environment tells you something about the efficiency of the external part of the perception action loop. So it is essentially something that we would expect that evolutionary pressures will have optimized. An actuator that does not change the world in the way the sensors perceive, or vice versa. Sensors perceive things that you can absolutely not change in the world, might be an evolutionary expense that you can save. Not always, of course, you can see much more than you can change in general, but still, The things we can see are usually things where we can point them to things we can change. So in other words, there is an evolutionary pressure towards well-equilibrated um, external push information, and we gave this the name empowerment. It's basically how much can you change your environment and actually detect this change. And this is a measure of how efficient your external perception action loop is. In general, you do not want it. This reflects essentially the adaptation of your perception action loop by evolutionary means, and therefore an organism will want it to be in a sweet spot, in a spot where this value is high, wants to maximize it. Finally, there's a measure that has been introduced by the group of Ralph Dare and Georg Martius. You had I and a couple of others, and that is predictive information. That is a different measure from the ones I discussed. It actually looks at the past and asks what can the past of an agent's experience predict about the future history, and trying to maximize that. Now, why would one want to do that? Remember, we talk often about the question about surprisal, minimize surprisal, and so on. Now, just minimizing surprisal creates a problem, the dark room problem. It means you can minimize your surprisal, go to a dark room, hide in the corner, and you can predict exactly what's going to happen, namely nothing. Now, that's not very interesting. You want actually something to be predictable. And therefore, you want essentially to have something to predict over. You want an unstable world, a world where what you do is precarious, where your future is not obvious. But on the other hand, you want it to be predictable from your past. So you have basically these counterbalancing forces. One, you want a precarious future, so it's an interesting future, something which creates a lot of richness in your world. But this richness is something you are able to predict. It's not complete chaos. It's not control, note, it's different from empowerment. Here, we don't talk about control, we talk only about prediction. But it's still mastery of the chaos. You want to have this precariousness under your, not control, but under your knowledge. So this motto by Bruce Lee is actually quite fitting. When we talk about these things here, these are basically intrinsic motivations, models of what could drive your behavior, even if it's not a particular goal. So I really like this motto. A goal is not always meant to be reached. It often says simply as something to aim at. And that's precisely what intrinsic motivations are. So basically, if you look at empowerment, I don't have time to talk too much about that in detail. It is about mobility. If you have a game, so many options, it's not actually carrying them out, it's just having them. Affordance, from basically Gibson's view of affordance, you can actually do things in your environment. If you look at transition graphs, you can consider this graph centrality. It's highly related to that. Perceivably different outcomes, efficiency divergence, basically the ability to create diverse futures, and in fact, it can be interpreted as an antithesis to learned helplessness, and essentially where you learn, oh, no matter what I do, nothing will change. It's the opposite of that, saying I can do things and I can make futures distinct by taking action. So I don't have the time to go to too many examples, but some results are well known by now. So you find the centers of maze, you find eigenbehaviors, which are preferred behaviors in a world. You can do pole balancing or survival games. You can use it to evolve sensors. As I mentioned, empowerment is actually a measure of the effectiveness, efficiency of your perception action loop. And so it's a very natural measure to evolve um, adapted sensors for your environment. And some classic examples are here. The Acrobot, basically double pole balancing. Lava World, which is a nice example. And here I will just show Pac-Man, where you have an agent that moves through the world and tries to survive. It's a classic survival game. And the Pac-Man has to escape the ghosts, which are very aggressive in this version of the game. The ghosts are in red, the agent is in yellow. And one thing that is really striking is that the agent manages to control the ghosts. Empowerment is about controlling what happens around you, and it controls the ghosts, and it actually pulls them behind it because it can predict what they are going to do. So in other words, it has a perfect model. It's not it's fully deterministic, but because it can control exactly what the agents are going to do, it actually trolls them in a way. It keeps them on their toes. It makes them do what it wants them to do, even very precariously, pulling them directly behind it, and it being quite dangerous if you had to react under time pressure. But the system has full ability to simulate the world into the future. Now, predictive information homeokinesis, I mentioned that already, is about a model that creates a rich future, a very precarious, unstable future, which is difficult to predict. But once you have your past, you can actually predict it. So you have precarious behavior, but it needs to be interesting. So it's not just predictability, it's predictability when there is actually something to predict. Just minimizing the future entropy is not enough. You just make it very small, and then it's an uninteresting world. You create a rich future entropy, which can be resolved by having a past. And this creates very rich um, behaviors, and I encourage everybody to look at the website by Martius and Dare, which has some really fascinating movies. Here I just give, I don't have any movie available, but I give some examples. So there's this band of individual robots. They don't communicate, they just have individual sensors. And this band learns to walk backwards and forwards. And there's no coordination. It just comes from this predictive information maximization drive. And here's another example with human articulation. So there's this robot with, I don't know exactly how many um, joints, I think something like 20, but something in that order of magnitude in different scenarios. You can hang it onto this high bar, and then it will try to behave like a human playing around with a high bar, putting in a pit. And if you watch these movies, it really looks like, okay, not very coordinated, but looks not random. It looks like perhaps a drunk or a kid trying to find out what it can do with its body. It's very clear that there's some coordinated behavior. Again, this is quite different from empowerment in its behavior, but it's still very, say, biology-like. And shows that using this type of scenario creates an interesting structuring of your trajectories through space-time. So as we talk about space-time, let's just consider what we just talked about. So if you look at the history, you have possible pasts, you have possible futures, and this is time, this is state space, if you like. And so you have a trajectory, and that is a given, that you have given that trajectory. And now when you look at empowerment, you're trying to maximize the futures. You can choose between these different paths, and as you choose between these different paths, at the end you have different futures that unfold from there. And you want these futures to be as different as possible. You want to find paths that separate these futures as much as possible. So these ones don't count that much, but these count as a relatively different because they don't overlap that much. These overlap much more. Now everything I'm showing here can be written in formulas. So I'm just giving here a qualitative description, but this can be formulated as basically a particular form of channel capacity of a very specific channel. And you can read that up in the work by Tom Anthony in 2014 IEEE journal. I forgot to put in the citation here, but you can contact me if you're looking for this. So this is counting separable futures. The more separable the futures are, the higher empowerment is. And empowerment maximization means you trying to maximize that ability to create different futures. If you do predictive information, it's not exactly what you're doing. There is no different futures you choose. Well, in fact, you choose an action, but the action is chosen in such a way as to maximize the richness of prediction. So there is a past, and there could be different paths, but there is one given path, and there's a process, and the process could go on in a certain way, but given that particular path, that process is being constrained. Whatever happens in the future is constrained, and the more you can constrain from the options that are available, you can constrain what you can predict about the future given the past path, the higher you predict information. That is what you're maximizing. This is about prediction, not about control. This is the difference to empowerment. And finally, I'm starting to move into the speculative part of my talk. You could ask the following question. Okay, there's a past, now we're in this state, and now imagine some ex machina action that you can do. You do actions that you cannot do as an agent. The agent does not have this possibility. In empowerment, the agent picks amongst the available possibilities to explore what's possible. In imagined alternatives, you don't. You have just possible imagined alternatives. Think of the Earth being moved to a different orbit or something like that. Things that are very, very difficult to do or impossible to do, but you can imagine that you could actually play around. And of course, this creates different futures in the different situations. And this is also a model for how you can consider a particular state in the world to be evaluated. Now, if look at that, if empowerment looks at drives that drive towards richness of visual futures. You want to maximize the futures you could generate. Doesn't mean that you actually exploit them. Each action sequence is a potential future. And so action sequences are generated potential timelines in the future. One of them is being taken in the end, but this is what you're maximizing. You're trying to create the maximum potential timelines. And in fact, you maximize your options, not the future complexity. You don't care about the complexity of the future, you just want to maximize the possible timelines that you can travel through. Predictive information is different. It drives towards uncertainty. It wants uncertain futures, but only if they can be actually resolved by looking at the past. So it wants, unlike empowerment, which wants control, wants to control what happens. In predictive information, you don't care about the control, you care only about being able to predict. And you don't want uncertainty for uncertainty's sake. You don't just seek out chaos. You seek out precariousness only if this is something you can actually resolve. But it's about prediction. It's not about what you can actually choose. Of course, the actions that you choose are those who maximize this predictive information. So your actions are chosen so that your prediction becomes powerful. The imagined alternatives is again a different picture, right? So you basically probe the possibilities from the varying present as ex machina. Things that you cannot do, you just imagine this is what I could do in this scenario. And this requires a complete model. To some extent, empowerment and predictive information also require models, but this requires a more powerful model. So in a way, I would structure the different perspectives we have taken, you can consider predictive information works through time because you have this prediction, you have the past, you have the future. Imagined alternatives looks through space. You evaluate possibilities, shift in space. What can you do when you shift your current situation in space? Space, not in the terms of Euclidean space, but space of possible states of your system. And empowerment is somehow sitting in the middle because you kind of can change what you're going to do, but it has still to happen in time. So it lives somewhere in this intermediary region between these two extreme cases. And with this, we can ask, and here comes my programmatic plan. We can ask about the nature of causality. Um, how shall we talk about causality? How shall we talk about agency as opposed to just being an object in a physical world? So, in other words, how do we transit from just something that just moves around the world to something that looks as if it has some agency over the world, even if we know ultimately that's a physical object, but we treat it as if it has this agency over the world. So, essentially, we have to think about every action you take as imbuing the future with value. an action that's taken by an agent that has evolved somehow, has been selected somehow, is creating value because every other action has not been taken. This is a powerful statement by the agent in terms of its decision how to symmetry break the future, the potential that the future has. Always keep in mind that choice has undergone evolutionary selection itself. So in other words, of course, this is not just happening because this agent magically has discovered it. It is a concentration of accumulated and crystallized knowledge throughout generations of billions of agents or 100,000 of agents if you evolve them in a machine that has decided what is the action that imbues the future with value. But what is the bottom line of everything we're talking about is that ultimately, when we look at the world, it's reflected in its agents. And with this, we close the loop to our original symmetry between the world and the agent. It's not a perfect symmetry. There is a very clear distinction between world and agents, but there's a surprising reflection of each other in the respective other side. And I'd like to close with a quote by Richard Feynman that nature uses only the longest threads to weave her patterns, so every small piece of her fabric reveals the organization of the entire tapestry. And of course, agents are a small but not insignificant piece of the fabric of nature. Thank you.